Well, good morning, good afternoon, good evening to everyone. Thank you very much for all the people joining this webinar today. Thank you very much for the International Water Association, and a big thanks to Gary and Stuart Hamilton for inviting AGANOVA to be part of this webinar series. My name is Ana Cozar, and I work in the business development team of AGANOVA. In this webinar today, I will be introducing the Nautilus technology, which is the technology designed by AGANOVA for leak detection in big diameter pipeline, in transport pipelines. And I briefly introduce also the NEMO platform, which is a project management platform AGANOVA has designed to optimize the work in leak detection campaigns. Having said that, and before I start with the Nautilus introduction, I would like to explain a little bit of our company. AGANOVA is a Spanish company. We are based in Malaga, in the south of Spain. The company was created about 11 years ago, and we started as being a leak detection company, offering leak detection services at local and national level. But after a short walk in the market, we realized that there was a need of technologies specialized in big diameter pipelines. This was the starting point of the Nautilus system, which was designed and produced at the beginning of 2016. And well, this was a big jump of the company, so we jumped to the international level and to be a company with a very, very strong R&D base. Since the creation of Nautilus, we have been focused in providing our technology as a manageable, affordable, and efficient solution for leak detection in big diameter pipelines. Moving to the description of the Nautilus system, Nautilus is a wireless, inline, and neutrally buoyant technology for water leak detection in large diameter pipelines. Nautilus is an acoustic methodology. So this means that, well, as many of you already know, the majority of the technologies to detect leaks are based in acoustics. This means that they detect the leaks and anomalies because of the sound they emit when the pipeline is pressurized. There is a specific frequency of these leaks, and that methodologies detect this frequency to be able to locate the anomaly within the pipeline. Well, this majority of technologies, they work from the surface. They capture, they follow the trace of they are located in the pipeline to be able to locate the leaks from the surface. And this is great for distribution pipelines or for small diameter pipelines. The problem with transport pipeline is that there are several obstacles that prevent the detection from the surface. For example, let me just mention that some materials are not good emitters of the sound, so they make difficult to find the leaks, or maybe the diameter itself of the pipeline is not a good transmitter of the sound, or just it's a matter that the pipeline is buried deep on the earth, so the leaks cannot be detected from outside. Considering this, we created the Nautilus system, which is inline technology. We introduced the leak detection system inside the pipeline to be able to detect all the leaks and anomalies from the inside. Nautilus then consists on a sphere that is inserted into the pipeline. The sphere travels free, driven by the water flow. And what it does, it captures the sound within the pipeline to be able to locate this frequency of the leaks. The sphere is extracted at the end of the section that we want to inspect with the help of a net. And when we extract the sphere, we analyze the information that has been compiled in order to be able to detect and locate the leaks. As we can inspect long lengths with Nautilus, for example, up to 35 kilometers in one inspection, we use one element in order to be able to pinpoint the leaks. This element is the synchronizer. More or less every 700 meters, we locate a synchronizer. This synchronizer is permanently knocking the pipeline, not when we are inspecting in the section. And what the sphere does, it captures the sound of this synchronizer, and they serve as a reference to pinpoint the leaks. It is important to take into consideration that Nautilus has been traveling free along the pipeline. All the derivation or branches must be closed during the inspection. I'm going to show you now and share with you a video which explains what I have just said. I think it can make you a clear idea of the functioning of the system. Well, before I move on, I'm so sorry, but I forgot to tell that if you have any question, you can type your questions in the chat, and I will reply on all your questions at the end of this presentation. Here, just to summarize a few key points of our methodology, Nautilus can inspect up to 35 kilometers in one inspection. As we detect leaks from very close to the leaking point, we can detect very, very small leaks as 0.005 liters per second. The error margin is 1 meter. We have to consider for the error margin that it's very important that we can position synchronizers every 700, and we have a good knowledge of the trace of the pipeline we are inspecting. It can be used in any kind of pipeline materials. As it flows freely in the center of the pipeline, it is designed to skip the majority of the obstacles that can be at the bottom of the pipeline. It can pass, it can travel vertically, of course. If the water passes, the sphere can pass vertical as well. It can work at very low water speed. We will go in the next slide for the minimum requirements of the system, and I will explain a little bit further. And it can be applied in pipelines buried at any depth. In order to perform an Nautilus inspection, we have to take into consideration a few elements. First of all, the water speed, the water flow. The minimum speed we need to be able to perform an inspection is 0.2 meters per second. The maximum velocity will depend on the pipeline diameter. Synchronizers. We need to locate synchronizers every 700 meters, but it is normally not a problem because we can locate the synchronizer in any point that is in direct contact with the pipeline. A hydrant, a valve, it just needs to be in contact with the pipeline we are inspecting. As an acoustic method, we need pressure. We need a minimum pressure of 2 bars so that the leads can emit a sound, and the maximum pressure supported by the system is around 20 bars. For the insertion and extraction, I will move to the next slide, but before I move to this slide, I would like to remind that the system is traveling free. So it is important that all branches must be closed during inspection. And if there is any configuration like a blind T or a Y, we need to know to be able to prepare the inspection. For the insertion, we need an operative gate valve of a minimum diameter of 80 millimeters. The insertion must be, this valve must be vertical to the pipeline we are inspecting. And to be able to do this when the pipeline is in service, what we do is we couple a pressure chamber on top of the valve. We insert the sphere inside this pressure chamber, and then we close the chamber, and then we are able to open the valve and push the sphere till it touches the flow of the main pipeline we're inspecting. For the extraction, is very similar. We need a gate valve, operative, of course, with a minimum diameter of 100 millimeters for extraction, and it must be vertical to the pipeline we are inspecting. Again, we put a pressure chamber on top of this of the valve, and once we have inserted the net, we can close the chamber, open the valve, and then push the net to the pipeline. The net it's formed of 2 flanges like this, and when they touch the bottom of the pipeline, they open. This net is loaded with a camera, which helps us to precisely locate the net, covering the whole diameter of the pipeline. Okay. And then when we have extracted the sphere and we analyze the information, we are able to detect leaks. We can classify them in small, medium, and big leaks, bubbles, and air pockets, and we can identify other anomalies. When we detect something that is not normal within the pipe, within a pressurized pipeline, we mark this point as an anomaly to make the client aware that maybe it worth to take a look to these points. And I think maybe all of you are very familiar with the sound of a leak, but let me just share here what we detect when we detect a leak. I'm sharing the sound. This first sound, you have heard a beep, beep there. This beep is a sound emitted by the sphere. This sound helps us to detect the path of the sphere at determined points. Now we are going to hear a tock, tock, tock. Oops. This tock, tock, tock is the sound of a synchronizer. And now we are going to hear the frequency of the leak. Sorry. situation, as you can imagine, the synchronizer was very, very close to the leaking point. So it was, in this situation, it was a partially open valve, and the sound was not a real leak, but an open valve. Okay. Just to, as I mentioned at the beginning of the presentation, we are based in Spain, but we travel at international level. Here is to give you a little bit of information on how the time needed for us to plan and perform an inspection. Normally, once we agree an offer, when we agree a contract, we need 1 month to mobilize to the country and prepare the inspection. These 3 weeks initial are to pre-inspection works and mobilization of the equipment and the team to the country. The field inspection takes 1-2 days, depending on the length of the pipeline we are going to work, inspect. And after the field inspection, we can emit preliminary results in 48 hours. And the final report of the inspection we have done is delivered in 5 working days. With regards to the field inspection, to let you know a little bit a rough idea of how it's performed. Normally, the installation of the insertion, the extraction point takes around 1 hour or 1 hour 30 minutes. Synchronizer installation takes an average of 20 minutes each. The insertion system takes about 45 minutes to insertion, and the removal of the equipment takes around 1 hour, 1 hour, 30 minutes. So this means normally that we perform 1 inspection in 1 working day. Finally, I would like to finish this presentation showing you a couple of examples of works that we have performed with the Nautilus system. This first case study, it was one of the first jobs we did here in Spain. It was a pilot project with the Suez Group. This was a pipeline that was passing by the middle of the middle of a city. So there were many obstacles for leak detection in this pipeline. First, the amount of external noise in the pipeline, the sounds of the city. Then, secondly, it was the bad access to this pipeline. It was It wasn't easy to sectorize this pipeline. And third, the pipeline was very, very, very old. This pipeline was 12 kilometers long, and it was in the city of Murcia, here in the Levante of Spain. The insertion was performed in a 150 millimeters valve, the same for extraction. And in this situation, we have to locate 18 synchronizers. After analyzing the information we collected during the field inspection, we found 21 leaks in this pipeline. 3 of them were very big, 8 medium, and 10 small leaks. Second case study is one of the biggest projects we are developing at the moment, because it's still ongoing. This project is a project in Qatar. And it is about inspecting 700 kilometers of pipeline. The duration of the project stated by the client at the beginning of the project was 3 years. So to give you an idea of the results of the inspection we have done, in the interim report of this project, that it was done in the month of May, the water loss detected was a value of 537,000 euros. So let's move here, per year of water losses in a distance inspected of 550 kilometers. So it wasn't the whole length, just the Two-thirds of the length covered, and all these savings were already achieved by the clients. These amounts of losses were found through 91 leaks, but additionally, we were able to find 188 incidents between anomalies and arc pockets and air problems within the pipeline. The results of our inspections were shown before by PDFs. I think when we did an inspection, we developed a report in PDF, and at the end of this the job, we delivered this report to the client. But we have also moved and give our own step for the digitalization of the water leak detection campaigns. This was the development of the NEMO platform. This platform is designed for the practical and effective monitoring of the leak detection campaign. So it is not just about the results, but it's the planning of the group, the execution of the services, and also sharing the results. Our clients will always have access to this platform to come back in the future and check the previous results of leak campaigns. The main characteristic of these platforms are that it has been designed to work operative, so it's very easy and intuitive. It allows the creation of different users profile from management to technical team. It is dotted, of course, of strong security measures to protect the data of the client, and it allows to have all the information about a project in one single work environment. Of course, allows the constant communication between AGANOVA technical team and the client technical team. And I think, yes, I'm just about to finalize this presentation. Of course, please send all the questions, all the information that you missed. You can ask in the chat, and I will try to reply. But in this last slide, I would like to share with you the efforts of AGANOVA to improve our system. We have developed a testing site in our facility where we can try and prove all the possibilities of Nautilus system, but also other technologies that we explore continuously. And of course, our R&D department is working to improve the system. At the moment, for example, our technical team, our R&D team, is working to add more sensors to the sphere, so we can offer a wider range of information to the clients. I hope to have this news soon for you. And basically, it was of course, Nautilus System is certified to be able to work in potable water by NS 61, and we have the ISO corresponding certificates. AGANOVA also and the Nautilus System belong to international association as One Water in Europe and Isle, and our system is patented in 68 countries. So Gary, I think, these are some clients we have worked at international level. So Gary, is there any question?
Okay, thank you, Anna. That was a good presentation. And as Anna mentioned, if anybody has any questions about the AGANOVA systems, then you can type them into the chat box. I was interested in the first case study that you presented, Anna. You were talking about some of the leaks being different sizes. So can your system sort of differentiate on leak size, or how do you determine whether it's a small leak, medium leak, or large leak?
Okay, the establishment of the leak is in basis of the inspection. We cannot quantify the leaks by the acoustic sound, but comparing the leak rates within one inspection, we can determine the size of the leak.
So it's not based on the noise that you hear or anything like that?
It is based on the noise. The technical team studied the different parameters of the inspections as pressure, velocity, and the different leaking points in this pipeline, so they can differentiate them between small, medium, and large leaks.
Okay. One of the things you talked about, some of the different criteria such as flow rate and pressure, but one of the things I didn't see mentioned was the pipe diameters, the range of pipe diameters that you can do. What's the minimum size that you can go down to?
Yeah, thanks, Gary. It's quite important to mention that we can work from 250 millimeters till 1,600 millimeters. The maximum, we can inspect pipelines bigger than 1,600 millimeters, but we have to plan an extract point different than our net. Our biggest net is for 1,600.
Okay. But 250 millimeter is the smallest, yeah?
Yeah.
Right, okay. There's a question from Stuart, which is, hi Anna, have you lost any balls and how did you retrieve them?
Okay, yeah, we have lost speed. Here it is important to mention, and I always repeat the same. The sphere it's traveling free, so it's inserted by a point and extracted by second point. So important thing to mention, which is very funny, but the sphere cannot disappear. So it is important when we are planning an inspection that we do an in-depth study of the pipeline, so we avoid to lose the sphere. And if the sphere is avoided, we know exactly how to rescue them. So there is a rescue plan. The rescue plan is based on the pipeline drawings, and also this sound I mentioned that the sphere emits, so it allows us to detect the sphere from outside.
Okay, we've got a question from Nabil, which is, it goes back to the estimating of the leak rate. Yeah. And they're asking, what is the accuracy of that estimation? Is there any accuracy around it?
I'm sorry to say that I haven't got a rate of accuracy. So when normally when the client excavates the leak, we compare our results with the result we have. But I'm sorry, I haven't got like a percentage of accuracy of this rate.
Right, okay.
But I write it down. There is another KPI I have to work in. Thanks, Nabil.
Right, okay. I saw on one of the slides you said that the maximum distance was 35 kilometers. What affects the maximum? What is it that makes that the maximum? Is it the time or the battery life, or what is that?
It's mostly a human factor. Of course, it depends. If the water speed is low, we will have a very, very long inspection. If you take into consideration that we have the insertion and extraction allocation plus the navigation, it could be you have to plan 8-hour navigation to make it like human affordable. This is the most important limit. The battery length depends on the kind of inspection we're doing, but will be around 24 hours of the battery life.
Right. Okay. So it's more to do with time, I suppose, and having people sat around. But also, you would probably need you'd need more synchronizers. Is that right?
Yeah. Synchronizers are to be positioned every 700 meters. So you will be locating asynchronized third every 700 meters.
Yeah, okay. So would you say it's better to do several smaller lengths rather than one really long length, or what is the pros and cons of either option?
If we have a very accurate information of the pipeline we are inspecting, so if it's a very clear distant length of a transport pipeline without a lot of different, for example, T's, blind T's, potential, if the client doesn't know very well the pipeline, and we can encounter elements in the middle of the pipeline that block the path of the sphere, we recommend to do shorter sections if we haven't got a good knowledge of the pipeline where we want to inspect, to make sure that we can cover all these distances. If there is a good knowledge, of course, it's better to do in one inspection because it's more cost effective and time effective.
So the knowledge of the pipe network is key to the success, I suppose.
Yeah, it is very important, as we are introducing the sphere, and we have to make sure that the sphere can pass along the length we are inspecting to be able to extract and of course analyze information and to be able to give results.
Okay, thank you. We don't have any more questions at the moment, so thank you very much. I see that you've got the info email address there on the screen. So I suppose if anybody has any more questions, they can email you directly.
Yeah, perfect. And I will receive this information through the info, so it goes directly also for me.
Right. Okay. Okay, Anna. Thank you very much.
Well, you are welcome. I'm really happy of being able to share this information with you today. If there is more doubt or comment, please contact me. I will be very happy to reply.